Okay, since we want to use oxidizing titrant, right? So what are the common ones? The strength of an oxidizing agent depends on the E potential, right? The E naught. So the higher one, the stronger. But that depends on your need. You know, if 1.09 is high enough to oxidize your analyze, then this is readily available. Then you don't need another one. So it all depends. So here is some common knowledge because these are very common oxidizing agent to use for titration. So when people ask you general knowledge, then you would quote potassium dichromate, potassium permanganate would be good chemicals to use, and then this is just 4+, right? So iodine is a good one to remember for. So these are quite common, right? Except the cerium 4+. Okay. Then whenever you have a titrant, that is your known solution in a burette. So you need to prepare with a known concentration. So you will need to realize whether these chemicals are primary standard or not. If not, then how can you standardize these chemicals? So here are the primary standards. It turns out, for example, potassium permanganate is not pure enough to qualify as a primary standard. So instead, these, sodium oxalate, arsenic oxide, and iron wire. Then among these, cost-effective and safety concerns together, then you will pick iron wire. So that's why in many laboratories, people keep a good roll of iron wire in desiccator, avoid rusting. Okay, then you can use that as a primary standard and standardize. So here will be a redox reaction in standardization. Okay. Now the indicator, whenever you do a titration, you need to have an indicator, right, for color change. So in this particular case, permanganate is a purple solution that you remember seeing. So itself functions as an indicator, right? Once you have a little excess of that, then your solution turns purple. Okay, so remember the potential, the half reaction potential is 1.51. So that represents the strength. Then cerium 4+. This is a strange chemical, but it's a good primary standard. Then again, for choices, right? Iron wire, so cheap and good. So that's why just keep that in the lab for multiple purposes. And then a particular indicator, then that is the strength. In different acids, then you get a slightly different strength. So the table will specify that. Okay. Now this is a common one. The beauty of that is itself is already pure enough as a primary standard. So, and it's readily available, and therefore it's quite common used in titration. Now you need a particular indicator with this name, and this is the strength. So between potassium permanganate, this one is convenient in a way that itself is indicator. And here, you need to purchase and prepare for another indicator, So it's a trade-off kind of thing. And the strength. Usually is the strength primary concern. Finally, the iodine, whenever, if that low potential is good enough for you, then you use iodine, so you don't have to mess around with all the real chemicals, right? So iodine itself is good enough. At room temperature is a solid, right? So you can weigh that out. And starch is cheap, everything is cheap. Yeah, you can even eat it for radiation protection. Eat a lot of seaweed. Don't eat chemical.
So how do we protect ourselves from radiation?
All of a sudden, Jeffrey. Oh yeah, current news.
Yeah, they had a meltdown.
Like the Japanese government distributed potassium iodine to residents nearby the plants. So Ki, you can basically the I, right? So iodine, seaweed get a lot of iodine. So you start eating a lot of seaweed.
So Dr. Austin is saying it could be brought over in the jet stream. California.
It's a bit too far, the Pacific Ocean.
For radiation?
Yeah.
Too far away, what diluted. Although the Earth moved to our direction, east to west. so it kind of translating to, the explodes here, then we meet it, we meet it right here. Yeah. It's seaweed.
Just don't eat Japanese seaweed.
Eat a lot of seaweed to get that about 300 milligrams. Enough iodine, right? Wow, eat whole pounds of seaweed.
How much are you getting paid to say this?
Huh?
How much are you getting paid to say that to eat seaweed?
Oh, the seaweed company?
Yeah.
It's free sushi. Okay, so now you are ready to do titration, right? Then you need to identify the titrants to your analyte. So this is a complete reaction in your titration. As an example, so you use serum 4+, then that is your titrant. Then you need to balance the equation for titration. It's very important. You know the coefficient, so you can do the calculation. So in this here is 1-to-1. Anybody can do 1-to-1 calculation. But then if you use this guy for titration against it, so your calculation becomes more challenging, right? So this could be a reason that you pick serum 4+ instead of the dichromate in your titration. But then this is not a big deal, right? You can balance this, and then the calculation will be based on this. Okay, so here's the point. If you're afraid of calculation, then you use 1-to-1 reaction. Although that is not a good reason for a good analytical chemist, right? So once you finish one calculation, it's good for life, right? So try your best with knowledge, balance the equation. So between titrant and your analyte is 6-to-1 mole ratio, okay? So with a known reaction. So this is your known reaction, balance. Okay, let's say for application, you have picked this particular reaction, so you are not afraid of 1-to-5 combination, and this is a good titrant 4, so balance for this complete reaction. Now, application in real sample is not perfect, it's not laboratory clean water solution that you can react right away neatly. But in real world, most likely you're going to use HCl to digest your sample. So there will be HCl in your titrating solution. So how does this interfere? Okay, HCl in your the titration reaction. So this is the reaction. The HCl will react with your titrant. So remove the titrant rather than allowing the titrant to react with your analyte. Okay, so the HCl will remove your titrant to form that. So this is interference. So once you know potential interference, you want to avoid, okay, at least minimize. So a proper procedure is once you digest your sample in HCl, boil it for enough time, usually 10, 15 minutes. Then it will expel. HCl is volatile, so it will expel the HCl. Then you use a reductor column. Okay, so your solution, your digested solution contains iron, and you want to ensure all the ions are in one oxidation state. Never assume anything, right? So once that is done, then you just cool to room temperature, pass through a reductor columns. Then after this, then you have increased your confidence, right? Then all the analytes in one chemical state, then that can proceed with the calculation, with the titration. Okay, so these are real world processes.